Have you ever wondered how your favorite apps or websites can handle millions of people all at once and just not explode? Well, the secret is this amazing piece of tech called a load balancer. Today, we are going to pull back the curtain on this unsung hero of the internet.
To really get this, let's just paint a picture. It's Friday night. That huge new show just dropped on Netflix. Millions of us hit play at the exact same second. How on earth does the whole system not just buckle and crash? That insane sudden spike in traffic is the very problem that load balancing was born to solve. Back in the early days of the web, things were a lot simpler. All of those millions of requests would have been pointed at just one single server. And as you can probably guess, that server gets totally overwhelmed, like instantly. It becomes what we call a single point of failure. And the result is always the same, a total system crash. So how do we fix this complete mess? Well, this is where the hero of our story comes in, the load balancer. It's this really elegant solution that sits right between all of the users and the servers, and its whole job is to prevent that catastrophic overload. So what is it exactly? Well, at its core, load balancing is the process of distributing all that incoming traffic across a whole group of back-end servers. You might hear it called a server farm or a server pool. The goal is super simple. Make sure no single server has to do all the work and gets totally overwhelmed. This right here shows the after picture perfectly. See, instead of everyone hammering on one server, all the requests first go to the load balancer. The load balancer then acts like this incredibly efficient traffic cop, pointing each request to one of the many available servers, spreading that workload out nice and evenly.
And the whole reason we do this is to hit a few really critical goals. We want the app to have high availability, which just means it's always on. We want it to be scalable, so it can handle those huge traffic spikes. We want fault tolerance, so if one server dies, who cares? And of course, we want low latency to make sure the experience is super fast and smooth for you, the user.
Okay, so we get it. The load balancer directs traffic. But how? How does it decide where to send every single request? This is where it gets really cool, because there are different strategies, and the one you choose depends on what the load balancer can actually see inside the request.
So load balancers really come in two main flavors. Over on the left, you've got your L4 balancers. These are the speed demons. They operate at the network level, so they're incredibly fast, but also kind of simple. They only see basic stuff like an IP address. But on the right, you have L7 balancers. These are the smart ones. They operate way up at the application layer, which means they can actually read the content of the request, like the specific URL you're trying to visit, and make much more intelligent routing decisions.
So once the load balancer knows what it can look at, it needs a strategy, an algorithm, to decide which server gets the next request. You can think of these as the different playbooks that our little traffic cop can use.
The simplest one by far is called round robin. It's kind of like a host at a restaurant, seating people one by one at each table in order. The first request goes to server A, the next to server B, then C, and then it just loops right back around to A. It's simple, it's fair, but it does make one big assumption, that all your servers are created equal.
But what if they aren't? What if some servers are just busier than others? Take a look at this chart. Server A is juggling 5 active connections, while server B is just chilling with only 2. A simple round robin might just ignore that. But this is where a smarter algorithm called least connections shines. It actually looks at the current workload and sends the new request to the server that's the least busy. In this case, server B for sure.
And then there's this one, consistent hashing. This is absolutely critical for any app where you, the user, need to stay on the same server for your entire visit. The classic example is a shopping cart, right? You don't want to add an item to your cart, hit refresh, and suddenly get sent to a new server where your cart is empty. Consistent hashing creates this session stickiness that makes sure a specific user always gets mapped back to the same machine.
So as you can see, a load balancer is so much more than just a traffic router. It's really a foundational piece for building a system that's resilient, that's fault-tolerant, and that can actually handle all the messy things that happen in the real world.
This brings us to a classic system design interview question. We've spread the traffic out perfectly. Everything is running smoothly. But then what happens when one of those servers just dies? Does everything grind to a halt?
Absolutely not. And this is where something called health checks come into play. A good load balancer is constantly sending out little pings to all the servers in its pool, basically asking, hey, you still alive? If a server fails to respond, the load balancer immediately marks it as unhealthy. yanks it out of the rotation, and reroutes all new traffic to the servers that are still healthy. It's like the system's own immune response, handling failures before we even notice.
Okay, so our servers are protected from being overwhelmed. But let's follow the logic here. What happens if we get so much traffic that the load balancer itself becomes the new bottleneck? Uh-oh, we've just moved that single point of failure one level up.
Of course, engineers thought of that too. In any real-world production system, you would never, ever have just one load balancer. You'd have multiple working together in a redundant setup. If one fails, another one instantly takes over with zero downtime. The key takeaway is you have to avoid a single point of failure at every single layer of your system.
All right, let's bring all this home. Let's say you're in a system design interview and they ask you to define a load balancer. Here is the perfect, concise, polished summary of everything we've just talked about.
This right here is your golden answer. A load balancer is all about distributing traffic to make things more scalable and more available. Like we talked about, it can work at L4 for pure speed or L7 for smarts, using algorithms like round robin or least connections. And don't forget, modern ones also handle critical jobs like health checks and even security tasks. That's the whole shebang.
And finally, please always remember that in system design, everything, and I mean everything, is a trade-off. If you choose a fast L4 balancer, you're giving up that smart L7 routing. If you use sticky sessions, it's simpler to manage a user's state, but it can make it way harder to recover when a server fails. There is no single best answer. The right choice always depends on what your application actually needs.
So we've figured out how traffic gets balanced across a bunch of servers in one data center. But that leaves us with one last massive question. How does a global service like Google or Netflix route your request to a data center on the correct continent in just a few milliseconds? Well, that's a whole other level of load balancing, and maybe a story for another time. Thanks for tuning in.